My talk is on the asymptotic solutions and high-order uniform difference schemes for perturbation problems for hyperbolic equations. This is a joint work with Professor Alaben Ashraliev. He is also my supervisor in PhD. Thanks for all his support so far. So in the first part of this study, I will introduce the asymptotic solutions, and then I will present the uniform difference schemes for perturbation problems. In the first part, the abstract non-local boundary value problem with non-local conditions here for hyperbolic equations with a self-adjoint positive definite operator A in a Hilbert space H, and then arbitrary small parameter multiplying the highest derivative term is considered. And the asymptotic solution to the problem is presented, and a uniform high order two-step difference scheme corresponding to this problem is obtained. So this work covers the general perturbation theory of uniform difference schemes on the hyperbolic PDEs. And in the last section, we will present the numerical implementations and numerical results of these theoretical statements, which support our theoretical results. So in the first part, introduction, and then I will introduce asymptotic formulas. Then I will present some abstract applications of these theorems and the results. And in the second part, I will introduce high order of accuracy uniform difference schemes and applications about the theoretical results, some abstract applications. And in the last part, I will present the numerical analysis. So the theory of singular perturbation problems is a developing research field, and this type of problems are growing interest to mathematicians, physicists, and other researchers. So these problems arise in various areas such as quantum mechanics, fluid dynamics, solid mechanics, reaction diffusion processes, aerodynamics, etc. So the role of asymptotic methods in studying the solutions of various problems is significant. For this part, for the asymptotic problems, I refer to the Kato and then Lomonov and Ilin and Ashraliev, Sobolevsky and Ashraliev, Batorini, and some more references. So the uniform stable difference schemes for differential equations with a small parameter in the higher order derivative has been investigated by many authors. Note that all classical difference schemes for differential equations with a small parameter in the higher order derivative are not uniform in epsilon convergence. In general, uniformity in epsilon convergence is not always possible. So from this very disappointing result, it follows the significance of the construction of the uniform difference schemes with respect to the small parameter epsilon in the highest order derivative. So we refer Ilin and then Shishkin and Ashraliev, Titov, and many references in these books and publications. So the high order of accuracy uniform difference schemes for parabolic, elliptic, and hyperbolic singular perturbation problems are presented in and studied in references below. The well-posedness of these different schemes were investigated in various Banach spaces. In modeling some physical phenomena and problems in engineering and classical boundary conditions cannot describe the phenomenon precisely. Therefore, mathematical models of various phenomena they often involve non-classical conditions, which are usually identified as non-local boundary conditions. And these type of conditions project the cases when the data on the domain boundary cannot be measured directly, or when the data on the boundary depend on the data inside the domain. In this type of problems, non-local boundary conditions involved. So in the present paper, we consider the non-local boundary value problem, abstract problem 1, in the Hilbert space with these conditions. So a function u of t is called a solution of problem 1 if the following conditions are satisfied. U of t is twice continuously differentiable on the segment. The derivatives at the endpoints of the segments are understood as the appropriate unilateral derivatives, and the elements u of t belongs to the domain of A for all t in the closed interval 0t. And the function u of t is continuous on the segment. And u of t satisfies the numerical conditions in problem 1. Here, in this study, an asymptotic formula for the solution of problem 1 with a small parameter epsilon is established, and the high order of accuracy two-step uniform difference schemes for the problem 1 are presented, and convergence estimates are obtained. For the asymptotic formulas, it is well known that we refer to Fattorni and Piscaria and Shaw. For the self-adjoint positive definite operators in a Hilbert space, we have the following inequalities hold. And here C of t is the strongly continuous cosine operator function, and S of t is the strongly continuous sine operator function defined by the following formulas. And from these formulas, we have these 2 and 3 are the follow identities for these operators. Now, let's consider a lemma which will be useful in the sequel. We have here alpha and beta are the coefficient of the non-local conditions. So with respect to these conditions, we have the inequality 5 holds. And it is well known that if u of t in domain of A and u prime of t in domain of A to the 1/2 and f of t be continuously differentiable on 0t, there exists a unique solution of the initial value problem with formula 7. So formula 7 is the solution formula for problem 6 with the arbitrary small parameter epsilon multiplied with the highest order derivative. So for this problem, we have the following lemma. Using the solution formula presented in 7, we can write the initial conditions u of 0 with 8 and the other initial condition with the formula 9. Here you see we modify the initial conditions with respect to our non-local boundary conditions, alpha and beta, coefficients alpha and beta. Now our main theorem on the asymptotic formula for the solution of problem 1 is theorem 1. Suppose that the function f of t has 2n plus third order derivatives and inequality 10 holds. Then for small epsilon and even number m, here this is even number is in detail. Here, even number m, the following m plus second order asymptotic formula 11 holds for the solution of problem 1. And for small epsilon and odd number m, the following m plus first order asymptotic formula 12 holds. Here, for the problem 1, we have the following equations in the third statement of the theorem. which we have the relations with U0, U1, and Vi and omega I with equations 13, 14, 15, and 16. And also 3 more equations with respect to this. Next, I will present applications about this abstract theorem. We present some applications for the firstly, we consider the perturbation problem 20, where a of x, phi of x, psi of x, and f of tx are given sufficiently smooth functions. And epsilon is the arbitrary positive number satisfying these inequalities. Here, for this problem, we have the following corollary. In this corollary, the formula is almost the same, but in this norm space here, we are in L2 space, in L2, 0L, with the formulas 21 and 22, with the following equations in the statement of theorem. Here and in the future, M is positive constant. So the proof of this theorem is based on the abstract theorem 1 and on the self-adjointness and positivity in L2, 0L of differential operator A. The operator is defined by the following formula, with the domain given in the Sobolev space W to end, with the following estimates on the cosine and sine operators. In this presentation, I didn't put proof of theorems. Some are long and I don't want to take your time with the proofs. And second, we consider the non-local hyperbolic perturbation problem with involution. Here, for the involution in minus L, the interval minus L to L, and here the involution conditions. This problem, the elements of the problem satisfying the following conditions. And we have the following corollary for the involution problem in this L2 space from minus L to L. This time it is in minus L to L, with the following formulas hold. And for the proof of theorem 3, it is the proof of this theorem based on the abstract theorem, proof of abstract theorem 1, on the self-adjointness and positivity in L2 minus LL, this time minus L to L, on a differential operator with the following operator given in the with the domain, and the following estimates hold. For this, we refer to Ashralif and Sarsenbi for their publication 18. And third, we consider the m-dimensional bounded open domain with the smooth boundary. And we consider the non-local problem satisfying the following conditions. So we have the following corollary in this L2 omega is our domain, and the following conditions satisfied. So this theorem of this corollary is also based on the proof of abstract theorem 1 and the self-adjointness and positivity in L2 omega of the differential operator given by 34, and with the domain given here, and estimates 35. Fourth, the domain is 0 t closed interval to omega. We consider the non-local multi-dimensional hyperbolic perturbation problem And this problem 36 satisfy the following conditions. Here in the conditions you can see this normal vector p to the omega. And we have the following corollary. Suppose that the assumption of theorem 1 holds, then the asymptotic formulas hold for this problem as well. This theorem, the corollary of this theorem, also based on the abstract theorem 1 and its proof. In this domain, we have the following operator with the given domain in the below. So asymptotic formulas are in this form, and now I want to talk about the uniform difference schemes which are constructed for the perturbation problems. So the first order of accuracy absolute stable two-step difference scheme for the numerical solution of 1 when epsilon equals 1 and alpha beta equals 0 was presented and investigated for the first time by Sobolevsky and Chebotaryeva in paper 90. It is in Russian, this paper. So absolute stable two-step difference schemes for the numerical solution of this problem when epsilon equals 1 were investigated for local and non-local hyperbolic problems very deeply. We can refer to Ashralif and Sobolevsky, their book and their publications, and our colleagues also. Now we will introduce high order of accuracy uniform difference schemes for the approximate solution of non-local boundary value problem 1. The first and second order of accuracy two-step difference schemes for the approximate solution of problem 1 when epsilon 1 were presented and investigated in 20. These difference schemes cannot be used in the general case. Moreover, it is well known that in general, no classical finite different approximation leads to uniform convergence with respect to epsilon. In general case, this is as far as we know, no classical finite difference approximations. So this arises the question whether there are any difference schemes which are uniform in epsilon. The answer to this question for the approximate solution of the initial value problem with an arbitrary parameter epsilon square at the derivatives was given in 25. This is, we refer to Ashralif and Fattorini, their publication in SIAM in 1992. In fact, in that paper, the high order of accuracy two-step uniform difference schemes for the approximate solution of the initial value problem with an arbitrary parameter at the derivative were presented and investigated. Uniform difference schemes for the approximate solution of non-local boundary value problems 1 are not investigated yet. In that publication, the initial value problem is studied, but for the non-local boundary value problem, not studied yet. This is our study, present study is on this subject. So the main result of this section gives an answer to this question for the approximate solution of this problem 1. The high order of accuracy two-step uniform difference schemes for the approximate solution of problem 1 are presented and their uniform convergence to epsilon is established. Here we consider the uniform grid space on the segment 0t with the following with time step tau. And let us denote tau equal rho times epsilon. So applying the formulas, these are 2, 3 are the formulas for the formula 37. Here C of K rho are the coefficients in non-local boundary conditions, and in 39 the U prime of 0. And here f sub 1k and f sub 2k are given by the following formulas. So applying these formulas, we get the following exact two-step difference scheme for the solution of problem 1 given by 40. And the initial conditions U0, 41, and the other condition here, these are, you can say, U sub 0, not U0, U sub 0 and U sub 1 in the difference case. And applying the exact two-step difference scheme 40 and 42, we construct the high order of approximation two-step difference scheme 43 with the initial conditions, not initial conditions, maybe with omega 0 and then in 45 omega 1. But these are derived from the initial conditions. Here f sub 1k, f tilde sub 1k and f tilde sub 2k are given with the following formulas. And here the coefficients in the formulas are present like this. We use in the proofs, we use Tyler and Maclaurin series, so we have the following expressions. So this problem is uniquely solvable and the following formula holds. So this is our solution formula 64 for the non-local boundary value problem. And for the convergence of this problem, we have the function f of t. Suppose this f of t has m plus first order derivatives satisfying the inequality. Then for the solution of difference problem 43, 45, the following convergence estimate is valid. It is 47, where m does not depend on tau and epsilon. So by this theorem, we prove that the convergence of this uniform difference scheme with small parameter is obtained. And here, this is the corollary theorem under the assumption of theorem 6 for the solution of difference problem. The following convergence estimate is valid in the domain of f. This is the maximum now. So I will present some applications of these abstract results. First, we consider the hyperbolic perturbation problem with non-local conditions. The discretization of this problem is provided in two steps. To the differential operator A generated by the problem 20, we assign the difference operator A sub h by the formula. This operator acting in the space of grid functions phi of h, phi h, satisfying. So it is known that this difference operator AH is a self-adjoint positive definite operator in L's operator. The problem 48 for the second order perturbation problem can be given. In the second step for this problem, we have the following corollary. Suppose that f of tx has m plus first derivatives in t and second order derivative in x in the operator in the space C. this inequality holds. And then for the solution of difference scheme for problem 48, the following convergence estimate 49 holds, where m does not depend on tau and epsilon. And in the same manner, the high order of accuracy two-step uniform difference scheme for the solution of hyperbolic numerical perturbation problems can be presented. Of course, such type of convergence estimates for the solution of these different schemes can be established. In the last part, I will present numerical analysis and some numerical results, numerical results of the abstract statements which we presented so far. So in the present section, in the first part, I will present asymptotic solutions and some results of numerical implementations. And in the second part, I will present the epsilon uniform difference schemes and their some results of numerical implementations. So we formulate a problem 51, but for this problem 51, we assume 50, the function 50 be the solution of the problem 51. And first we assume the function, we consider the function 50, and then using this function 50, we formulate a mixed boundary value problem 51. Assume the function 50 as in this problem. This is as you see, this is the small parameter epsilon square multiplied by the second derivative t, and then right side exponential minus t times sine x, and then operator a of f of t in this form, and the initial conditions are given with the following formulas. So for the solution of this problem, we use the asymptotic solution formulas of which we presented in theorem 1. These formulas, for the convenience, I put them again. I already present these formulas in theorem 1. These formulas are for the first one, m plus second order asymptotic formula. The first one for the small epsilon even number m. And the second formula is m plus first order asymptotic formula for small epsilon and odd number m. The second one is for odd number m, and the first one is even number m. So for the error analysis, the errors for the asymptotic formula are computed by the error formula 52. Here u of tx epsilon is the exact solution, and u tilde is the asymptotic solution of problem 51. And in the following tables, if m is odd, we take n equal m plus 1 in Matlab code, and the order is n. And if m is even, we take n equal m plus 1, then the same as before in Matlab code, but this time the order corresponds to m plus 1. Here's some technical details. And in the first table, using the asymptotic solution formulas, the error results for the asymptotic solution of problem 51 are the following. Here, epsilon values ranging from 2 to the minus 1 to the 2 to the minus 5. But for other epsilon values or smaller ones, also this formula works very well. Then the results are very good in all small epsilons as well. For n equal 4, n equal 6, and n equal 8, we have the following results. And for the same formulas, I also obtain the results for the epsilon ranging from m to the minus 1 to m to the minus 5. Different presented in the table. Here becomes smaller and smaller, then you can see the errors are decreasing uniformly. And we also present the line graphs in the following figures. We illustrate the comparison between the regular asymptotic approximations and the exact solution 50. And for epsilon 2 to the power minus 1, we take this epsilon in the figures. I take this epsilon 2 to the minus 1, because if I take smaller epsilons, then the gap between the exact and approximate solution becomes very, very small, and then they overlap. So I take in the first figure n equal 4 and epsilon 2 to the minus 1. Here, this orange line, orange curve represents the approximate solution, and the blue curve represents the exact solution in this line graph. And if you take epsilon equal 2 to the plus minus 10, you can see that the exact solution and the approximate solution overlaps, and they are almost the same. So this shows the efficiency of the asymptotic formulas. And I also consider another figure with n equal 5, and in this figure I take epsilon n to the power minus 1. We have the following figure. And if I take m to the power minus 5, a very smaller epsilon, you can see exact solution and approximate solution are overlapped. So in the figures, the curves are parallel and overlapped as epsilon goes small. So this indicates that the proposed scheme converges independently of the values of the perturbation parameter. So in the second part of analysis, I will present some results of the high order of accuracy uniform difference scheme. Many studies in the literature have been presenting numerical verification of the epsilon uniform difference schemes on the perturbation problems for specific type of hyperbolic PDEs. However, to the best of our knowledge, it can be shown in general that no classical finite difference approximation leads to the uniform convergence with respect to epsilon. So in the literature, we see many publications and many results, but in general, no finite difference approximation leads to uniform convergence. So in the present paper, the numerical realization of high order uniform difference schemes for hyperbolic problems in the general case, I want to underline this, in the general case, is presented for the first time. So we study the high order of approximation of the following formulas for the maximum point-wise epsilon uniform errors with 53, and then exact maximum point-wise errors computed with the formula 54. So in the formulas, the exact solution is denoted by u of tk, xn, and epsilon, and the numerical solution is denoted by u sub n epsilon for problem 51 at tk, xn, and epsilon. So the uniform difference schemes of the numerical solution of the initial problem 1 of differential equation with an arbitrary parameter epsilon at the derivative are the following. In the table 3, we present results of numerical implementations for the this table presents the computed maximum pointwise errors for the epsilon uniform high order of accuracy difference schemes 43 applied to the problem 51 for a variety of epsilon values that are given as powers of 2 and n values. So as you see, as in this table, we choose the values, epsilon values for the variety of powers of 2. As you see, as the epsilon gets smaller and smaller, then the errors becomes the uniform difference scheme converts, the difference scheme converts uniformly by these results, very small results. And another table for the same difference schemes, this time I take epsilon for variety of epsilon values that are given as powers of 10 and for different n values. This time in this table, error results for epsilon uniform difference schemes are presented here. Epsilons are for ranging from 10 to the 0, 10 to the power minus 20. And as you can observe, here the errors are very small. So this shows that the uniform difference scheme converts, difference scheme, high order accuracy difference scheme converts uniformly. So in conclusion, in the present paper, an asymptotic formula for the solution of this problem with a small parameter for the solution of the initial value perturbation problem of the hyperbolic type in the Hilbert space is presented. The high order of accuracy two-step uniform difference schemes for the solution of this problem are presented, and the convergence estimates for the solution of these difference schemes are established. We are interested in study of asymptotic formulas and high order of accuracy uniform difference schemes for the solution of hyperbolic non-local perturbation problems. 55 in the multidimensional case, and absolute stable two-step difference schemes for the numerical solution of problem 55 when epsilon equal 1 were investigated for local and non-local hyperbolic problems. We will investigate for arbitrary small parameter epsilon in the future projection of this study. So thank you very much for your attention.